So Jan, welcome and thank you so much for joining today.
Yeah, I'm happy. I'm looking forward to the interview.
Now let's talk about the company that you represent first. What is IQM?
Yeah, with IQM, we are on a mission to build world-leading quantum computers for the well-being of humankind. So what this means is we build full-stack quantum computers. We are using the superconducting approach, which is the kind of most widespread approach to build quantum computers. And then we are selling them to big computing centers or through the cloud. And quantum computing is a kind of new compute technology which holds the promise to speed up certain calculations, and this speed up can really be significant. So in kind of certain cases, a big supercomputer would maybe need thousands of years, and then a quantum computer could do the same in the order of minutes. And the kind of nice thing is that these are not just kind of scientific or theoretical problems, but you would find them anywhere in kind of new materials, pharmaceuticals, optimization of supply chain, finance, and many other fields as well.
Right. And so how far are you then in the process of building an actual quantum computer that would be useful for these practical purposes?
Yeah, so basically in the end, we are very similar to a chip company in normal semiconductors. So every year we tape out a new processor generation, which is more powerful than the previous one. So we started with 5 qubits, then we had 20, now 54, the next generation is 150, and so on. We have a roadmap that goes all the way to millions of qubits. And we think that what you can do today with these computers is mainly you can actually explore already new science. You can do things that with quantum computers that you cannot do anymore on big supercomputers, and you can do proof of concepts for many use cases. And we think that the first really commercial relevant use cases you will get with maybe a few hundreds of qubits and a kind of quality which is still a bit better than what we have. But then if you look at the roadmaps of companies, including ours, this would probably happen 2-3 years from now.
Right, I understand. And then there's the entire error correction issue, right? So is there a way so how do you approach it and how do you make sure that when it gets to hundreds of qubits, there will be useful qubits?
Exactly. I mean, the challenge with quantum computing is that the quantum bits that we are using, they always make errors. We can reduce the errors as much as we can, but there will always be some finite level of errors left, which is not a fundamental problem. You can correct for them. And the way you do this is on the chip, you bundle many qubits into one logical unit. And depending on which final kind of fidelity you want to achieve, probably the number of qubits that you need to bundle together is between 100 to 1000. So this means that, let's say, if you have a 1000 qubit chip, you can probably have a few logical qubits on them. And if you want to have a few hundred logical qubits, then probably you need kind of tens to hundreds of thousands of physical qubits on the chip. And the point is actually how efficient you can run this error correction. And there are many ways to do this out there, and we have actually developed a new approach which is based on low density parity checks, and with this we can reduce the overhead by a factor of 10 to 20. So we can actually build the same logical unit with around 10 to 20 times less physical qubits on a chip.
Okay, this is really interesting. So, and now you recently launched a 50-qubit computer in Finland together with VTT, right? So what is possible on a 50-qubit computer today?
Yeah, so this number, it's 54 qubits on the chip. You find it also in literature from other companies that have been building similar chips. And the interesting thing is that this is basically the threshold of what you can still simulate with a big supercomputer. So if you want to simulate the behavior of a quantum chip, you can use a supercomputer. And then if you increase the number of qubits, it gets exponentially harder and harder to do this. And the boundary of what can still be done is around 54. And this is why it's so interesting, because it's kind of the last thing that you can test. And in addition to this, you can do actually lots of proof of concepts. So you can run molecular simulations for, let's say, small molecules with maybe 10 atoms in it. You can run optimization problems for, let's say, train schedule optimization with, let's say, tens of trains or so in it. So these are the kind of proof of concepts that you can do, and we do a lot of this together with companies where they actually create quantum readiness. So they have in-house teams which want to build up know-how, build up IP, build up processes, and for this actually they get access to our quantum computers.
And when you talk about testing and the simulation on a normal supercomputer, does it mean that while you're building quantum computers of under 54 qubits, you would basically just check its behavior with a simulation on a normal, like traditional computer as well.
Yes, and that's very important, because in the end it's about also trust in the technology, because let's say if we go beyond 54 qubits, we are reaching a regime which you cannot anymore verify so easily with a normal supercomputer. So it's very important that in the regime of, let's say, 520 qubits, you make sure that actually the quantum processor really behaves the way you want it to behave, because this then lets you know that actually also for the larger processors, the result is trustworthy.
That's really fascinating. And then it also means that under 54 qubits, you can experiment with different ways for this computer to kind of self-test.
Yes, exactly. And of course, some things are easier to check and some others are harder to check. And actually, this is always the elephant in the room, but one application of quantum computers is the code breaking, which is a very asymmetric problem. So the way we do it right now is that usually we multiply numbers together, and doing the reverse is very hard. But if you kind of have the answer, it's very easy to check. So if you know the numbers that you need to multiply, it's very easy to do the multiplication, but the reverse is very, very difficult. And this is an example where actually you can test quite easily whether the quantum computer did the right thing or the wrong thing.
Right, I see. And if we were to try and make it simple, so a 50-qubit quantum computer, if we were to compare it to the history of traditional computers, what would it be? Would it be like 8086, like 386? Where are we?
Yeah, it's of course there are different aspects. I mean, if you look at the machines that we build, these are still kind of rather big machines. They don't look at all like your laptop computer, but they look more like the machines that we had maybe in the 50s and 60s, where there were racks full, and then there were people actually connecting the cables. So still our quantum computers, you see a lot of cables going in and out. So from this perspective, we are more in the 50s or
like
60s.
mainframe area.
When it was like this. Of course, the thing is that in computer industry, we have been now following Moore's law for decades, the doubling of transistors every other year or so. And with quantum computers, we are now actually trying to beat Moore's law in a few years, right? That's the challenge that we work on. And it's only possible because we have this exponential speed of computing power, and there's nothing kind of faster in nature than an exponential law. So it is clear that the quantum computers will outperform the regular computers. But of course, we are competing here with tens of years of development that has been put into the overall computing industry.
Yeah, and that brings us also to the argument that I wanted to put in front of you. I read a story, like an essay, I think, a couple of months ago about that quantum computing may be losing its relevance and its applicability just because generative AI can already do so many of the tasks that were initially considered to be only doable through quantum. Is this an argument that you have heard already, and do you have any take on it?
Yes, of course. I mean, I've heard the argument, and there are always skeptics. And it's good that there are skeptics, because you need to challenge the technology also to make sure that it develops in the right direction. But I think there are a few aspects. One is that even if AI could do everything, it consumes actually a lot of power, and it's very big machines, very big computers that we use there. So actually it would be great if we had alternatives on the processor side that help actually reducing the power consumption and also make it maybe more affordable. And this is something where quantum computers can help, because they are much more energy efficient than big supercomputers. But then there are still tasks actually which are very complex by nature, not very big. AI usually is based on the fact that you train these very large models, so there's huge amount of data involved. Quantum computing actually addresses different types of problems which are very complex from a mathematical point of view, but where the problem size is not that big. So the traveling salesman actually is a good example. You don't need that many kind of rivers and bridges to create a problem that is very hard to solve, to find the optimal path that you want to go. It's really on the order of tens, and from this perspective, there will always be a room for quantum computers to solve these very complex problems.
I see. Getting back to the event that we are at, EIC Summit, you have been chosen for the STEP Scale-Up program together with a few other scale-ups. So what does it mean? Like what's in it for you?
Yeah, I mean, so first of all, of course, the EIC supports kind of tech and deep tech companies in Europe which are relevant for the future, and they have been supporting us already for a long time, and we are very happy to have them on board through the accelerator program. Now with the STEP, actually they're going the next step, so to say, and they're going this next step in terms of technologies which are critical for sovereignty and other strategic aspects. And for us, of course, this is super important because it gives credibility to the technology that we are developing, and it shows the importance also that it has for Europe as a whole and for kind of the sovereignty and the wealth that we are going to develop based on this. And it's also, I think, a great instrument because it helps addressing the scaling and scale-up challenge that we have in Europe, that there are not enough big scale-up funds which can deploy actually larger tickets in larger investment rounds. So I think it's a great instrument that the Commission has developed together with the EIC to help companies like ours in their journey to scale up critical technology for Europe.
And what is the time frame for this funding?
So the way they do it is in a similar way they do it with the accelerator program, that they co-invest with other investors. So there still needs to be an external lead investor who is leading around, and there needs to be a proper due diligence process and all of this. So the timing actually depends on the timing of the funding round that these companies are going through. Some are probably already closer to finalizing a round, some probably still take some time. And I think the EIC is just following then the rhythm that the lead investor brings into these funding rounds.
And you, according to news reports, you're currently in conversations of also raising a 200 million round, if I'm not mistaken. So is that part of it? Is this going to be part of it?
Yeah, so we are currently fundraising. I cannot yet say what the final number will be because you never know until the fundraiser is closed, but yeah, it's going to be a big round. And indeed, the idea is that the STEP program then will feed into this new funding round.
This is great. And I also wanted to ask about your quantum computer, so the Radiance. So this is the 54 qubit models, right? So where are you on shipping them? So are there many orders for them? And like when are they going to be actually delivered?
Yeah. So right now we're shipping the 54 qubit system to a couple of customers. One was already announced in Finland, but we also have customers in Germany and in Italy and other places for the 54 qubit system. But we have sold already also 150 qubit systems. I think the first deployments will be in 2026. So we are currently working on the first in-house versions to kind of do the R&D and the different improvements that we need on the processor side, and then they will be deployed to the customers in 2026.
What does it take to actually manufacture a quantum computer?
I mean, first of all, and the heart of the computer is the chip, the quantum processor, and this is what we develop in-house. So we actually, we develop the overall layouts of the chips, then we also do the actual chip design with the design tools, so actually how the qubits look like on the chip, and then we do the tape out in our own chip factory. So we have built our own chip factory. It's the only private foundry for quantum chips in Europe, where we then do the tape out and the packaging of the processors. And then we act as a system integrator around it. So we buy actually a lot of third-party components, the cooling systems, the cables and other things, and we build a whole system out of it. And as said, these systems stay still. They're like 2 by 2 meters in area, and then they're maybe 3 meter in height. So these are larger systems. So it takes a lot of components, a lot of electrical devices and components in there to build a complete system. And then, of course, the whole software stack as well. Which is very important because this in the end defines the user experience, and we are actually investing quite heavily in the software stack and in integrating our quantum computers into supercomputing environments, also into the AI workflow that is currently being developed. So there's lots of work going on actually on the software side as well.
Do you have a goal of becoming an, let's say, integrated manufacturer of the entire sort of all the parts that are required to build a quantum computer?
Yeah, I mean, we see ourselves as a system integrator, and we don't produce all the parts ourselves. I think it's too complex and too much of a thing, and it's good actually that there's a whole ecosystem now building up, and the supply chain is actually really building up in many components where let's say a few years ago there was maybe one startup producing them. Nowadays there's actually a choice that you have, so there's actually much more strength and de-risked supply chain, which is great, and we see ourselves as a big system integrator then in the end.
And you mentioned integrating quantum computers into AI workflows. What does it mean in practice? So where is the place for quantum computing in the AI workflows, and actually vice versa?
Yeah. So generally we see quantum computing not so much as a standalone technology, but actually the future of computing we see is going to be hybrid devices. So there will be a quantum computer, there will be a cluster of CPUs, GPUs, maybe other compute modalities like neuromorphic computing in the future, and then a kind of an orchestration layer on the software side, which takes the big problem that you want to solve, and then takes this part that runs well on a quantum computer and gives it to the quantum computer. It takes this part that runs well on a GPU cluster and put it there. And this is the way to think about, for example, let's say an AI workflow, that even in these AI problems, there are actually kind of sub-problems which are quite complex from a mathematical point of view. So for example, what quantum computers are good at is multiplying big matrices, so linear algebra. And usually you find these kind of problems in an AI problem. And this is where the quantum computers can help. So we have lots of ideas how quantum computers can actually accelerate AI calculations. But then it's also the other way around. So actually, to develop our quantum computers and also to run and operate our quantum computers, we use lots of machine learning technology, for example. And so from this perspective, it's a two-way street. So on the one hand side, quantum computers will help AI, but on the other side, already now AI actually is helping quantum computing. And I think in this kind of synergy and playful way to do it together, both sides will benefit in the end.
Absolutely. And a totally different question, a topic that is discussed a lot here at EIC Summit and in general within the European technology ecosystem is the strategic autonomy of Europe, digital sovereignty, technological sovereignty, and of course quantum is a big part of that. So I would expect that generally the European authorities would be not happy, for example, if you were to sell the company to a US party, to a US acquirer. But is this something that you would do, for example, if the price were right? What is your take on sovereignty in general and on the possibility of the company changing hands and drifting towards the US?
Yeah. I think the current geopolitical kind of times show how important it is to avoid dependencies. I don't think that we should stop all trade with the US or other parts of the world. I think it's good to have a kind of global system, but of course we should be very well aware of the dependencies we have and de-risk them. So for example, have a second sourcing strategy so that there's always an opportunity to kind of source your components, let's say from a European supplier. And our goal is to be an active player in this, and I already mentioned we have our own chip factory which we run, which I think is a big part of the sovereignty topics, kind of producing again future chips in Europe, and we are investing still more into this. So I think this is very important, and I think we are an active contributor to it. Now, when it comes to kind of the future and also the future of IQM, our goal is actually to build up a sustainable business model. So I think we have very strong plans also from a financial perspective to build a profitable business out of it. Our sales numbers are increasing almost on a kind of monthly basis. The sales pipeline is strengthening a lot. So this is really our goal, to build up a sustainable business so that we kind of don't get into a situation where maybe we have to sell. I think it's always good to have opportunities, of course, and to look at them, but really our goal is to build here a sustainable business which doesn't change ownership.
But and also, is it your goal to stay a European company? Like, are you buying into this entire sovereignty and strategic autonomy discussion?
Yeah, I mean, I have been using in the past this kind of quantum Airbus example, and this is a little bit what we do is that we say actually the topic of quantum computing is too big to do it in only one country, or is also supported by only one country. Of course, we started in Finland. This is where we have our headquarters and most of the team and the factory. But we also have a very strong team in Munich, for example, where we do a lot of R&D work as well, especially on the error correction and algorithm side. And then we have actually also a team in France, and we have people in Spain and Italy. So we really see this as a European effort on the R&D side. But then we have global ambitions, and similar to Airbus, they are selling their airplanes not only to European airlines, but around the world, and this is really our ambition. And we have been selling quantum computers also outside of Europe. We have been, for example, selling in Korea, in Taiwan. We have been selling cloud to the US. So the goal really is to build a global business out of Europe. That's the idea.
Right. Jan, thank you so much. Thanks a lot for taking the time. Thanks for answering the questions, and good luck with everything you're doing at IQM.
Yeah, thank you. Thanks a lot.